Good afternoon. The MC just did exactly what I'm going to say. So my welcoming is very short. First of all, welcome Professor Stephen Barbas, Professor John Hawley. Guests, I imagine there are a lot of students here. There's some high school students as well. I hope you understand what is going to present to you. And our graduate students and colleagues, welcome to Hong Kong U. It's really a privilege for the university to host the two Shaw laureates on astronomy today, and to bring them on campus to interact with our students and colleagues. As the MC just said, the Shaw Prize was established some 10 years ago, and this is the 10th year of such awards. So the Shaw Prize has a 10 years anniversary. The prize consists of 3 areas: astronomy, life science and medicine, mathematical sciences, and each award with a monetary award of $1 million. The MC didn't say that, so I supplement the information. What has been done for 10 years is for the world to recognize top scientists in the world, and Hong Kong be part of this rewarding system, and Hong Kong should be very proud of it. Sir Rayleigh Shaw, who is also our honorary graduate, has been supporting Hong Kong's research and higher education for many, many years. He is one of the supporters in Hong Kong in this respect. So we would like to give him a big thank in promoting research and higher education in Hong Kong. As the MC or in your brochure, there's a statement of the contribution by Professor Barbas and Professor Hawley. I just read it. As important discovery of MRI. I'm an engineer, so when I look at MRI, I say, hey, this is something I recognize. I do medical imaging as well. So I say, hey, this is something I recognize. I should attend the talk and learn something more. However, this MRI is not the MRI I'm so used to. Medical imaging techniques that many of us know. This is magnetorotational instability. And it is a discovery to demonstrate that this instability leads to the turbulence that explain the phenomena in astrophysics, the accretion disk. So before the talk, I would like to prepare myself. So I Google and try to get myself prepared so that I'll learn a lot more, and I know very little about the subject. I was also in the Shaw dinner last night, sitting on the front row, listening to the two professors explaining the work, and this very nicely TVB documentary on their work. I sat there, paid absolute attention to what is being explained to us about the work. Afterward, I am absolutely clueless. Then I Google, of course, just half an hour ago in my office. So I find from Google, an accretion disk consists of gas in rotation about a central mass. The mass could be a star or black hole, so I understand that. When they are evenly slightly magnetized, the disks are extremely unstable to what is known as this MRI. This is the discovery. And this instability disrupts the gas and make it turbulence. This solves a long-standing problem in theoretical astrophysics and explains the underlying physical mechanism of this accretion disk. So this is still at my level understanding, and I hope to get more into it after listening to the two experts. There are also a few animations I would highly suggest you see. One of which is quite impressive is an animation made by NASA. You can find it in YouTube. Just type in MRI, the long word, not the MRI short form. And I watch it, and I'm still fairly clueless in what is that. So I better step aside and let the two laureates explain the exciting work to you all. Before I step aside, I have to tell you that while Googling, I bumped into a newspaper article called Salina Online Journal, published in Salina, Kansas. I am very much in tune with Kansas. I stayed in the Midwest for 20 years, Iowa, Missouri, Wisconsin. So when I look at the Kansas, of course, I flip and look at it. This is the city where Professor Hawley grew up. And while reading the article, it was an interview by the small town, I assume it's small, Salina, Kansas, on the Shaw Prize. And this one quotation really popped up into my head. Professor Hawley has described himself and his team of researchers as, "We are just selfless scientists who live for the joy of discovery." This is a good statement for all our students, secondary school and undergraduate and postgraduate. We are just selfless scientists who live for the joy of discovery. Of course, he also mentioned that it is nice to get some prize money as well. Quote unquote. So let's congratulate Professor Borbus and Professor Hawley on the cash prize and the deserving Shaw Prize for their lifetime of tireless research, most importantly, the joy of discovery and a great contribution to science. Thank you very much.
May I now invite Professor Sam Kwok, Dean of Science of the University of Hong Kong, to introduce our first speaker. Professor Kwok, please.
Good afternoon, everyone. First, let me welcome you all on behalf of the Faculty of Science. As you know that every year during the after the award ceremony, the University of Hong Kong hosts one of the three prize winners, and we rotate with the Chinese University of Hong Kong and Hong Kong University of Science and Technology around the three subjects. So of course, it gives me particular pleasure of having the astronomers for this year's lecture. Some of you may know that I also work in the field of astronomy myself. And as you probably heard from both the MC and Professor Chin, this year's winners were awarded for their work on accretion disk. So if I may, I just want to supplement a little bit on what Professor Chin has said, in case some of the members of the audience are not so familiar with the background. And accretion disk turns out to be a very common phenomenon in the universe. They are, for example, part of the mass transfer process, but you have a double star where mass is being transferred from one to another. They tend to form, gases tend to accumulate in a disk form, rotating, as Professor Chin has mentioned. And we have this kind of phenomenon in a center of active, nuclear center of active galaxies, as well as in regions that new stars are forming. There is also relevance, maybe also with our own solar system. We know our planetary system, our solar system, is a form of a disk, is rotating, or is more precisely differentially rotating. And what is the role of magnetic field playing in this process in terms of dissipating energy and transferring angular momentum are one of the major unsolved questions of modern astrophysics. And we're very pleased that this year's Nobel Prize of Astronomy going to the two speakers today, Professor Borbus and Professor Hawley. And let me say a little bit about our first speaker, Professor Stephen Borbus. He's currently the Savilian Professor of Astronomy at the University of Oxford in the United Kingdom. He was educated at the Massachusetts Institute of Technology, where he took his Bachelor of Science degree in both mathematics and physics, and in the University of California at Berkeley, where he got his PhD in theoretical astrophysics. He also held academic posts in at Princeton University, MIT, and University of Virginia. Before going to Oxford, Professor Balbus has been working in the physics department of École Normale Supérieure de Paris for 9 years. So his major area of study is astrophysical fluid dynamics, particular interest in magnetized gas. And so I hope today he'll tell us more about how these physical processes have influenced the development of accretion disk in all these circumstances that I previously mentioned, and maybe even in our own backyard in the solar system. So, for the purpose.
Let me start out by expressing my gratitude to the Shaw Organization and to Hong Kong University for making this truly joyous, wonderful experience. Not only has it been a model of efficiency, it's been a real pleasure to come with my family and to receive such a warm and interested welcome. It's really been a delight, and I'm very deeply grateful. I also thank Professor Sun Kwok for an excellent introduction. I'm not sure what I'm going to do now with my first few graphs because he touched on the subject so well. The first few minutes may sound a little bit repetitive to you, but that's all right. When I was a student, I was once given the advice that you should never underestimate the joy of an audience in hearing something that they already know about. So I'll take that to heart. So I'm going to talk about, as my title suggests, accretion disks. Give a very brief overview. 45 minutes, of course, is not nearly enough to do justice to the subject, so I'll have to race through it a bit. But I want to give you at least a taste of the variety of different accretion disks, why the accretion process is so fundamental to our understanding of the universe, the remarkable behavior of the magnetorotational instability, and then something which I think deserves more discussion, and that is that magnetorotational instability has been very important because it has allowed us to understand how accretion disks operate, but it also puts us in tune with a type of physics, the physics of weakly magnetized gases, that has ramifications beyond accretion disks. It helps us understand not just dynamical properties, not just rotational properties, but the thermal behavior of gases as well. And I'd like to see if I can get that across later on in the lecture. So, let's begin with the big picture. All structure in the universe, stars, galaxies, clusters, this is all created by the process of accretion. Without accretion, the universe would be very dull. It would be big, expanding, cooling gas, and that would be the end of the story. We wouldn't be here listening to this lecture. So, we need to form structure. Stars and planets form in gaseous cocoons of interstellar matter. Gas streams flow from one star to another in binary systems. So this is a different kind of accretion process, transference of mass from one star to another. Huge collapsed stars, black holes, sit in the center of galaxies and they draw gas from their surroundings. Once accretion gets going, it can't be stopped. The gas is either perhaps blown away by energy or radiation coming from the central source, but eventually the fate of the gas is to collapse, either to solids or to ultra-compact objects, white dwarfs, which are held together by degenerate pressure, in effect a big atom, neutron stars, I should say electron degeneracy pressure, neutron stars held together by the same, or supported against gravity by the same type of pressure, the this time in the neutrons, in effect a big atomic nucleus, or the ultimate collapse, black holes puncturing space-time itself. So, though accretion once started, it can't be stopped. It is not so obvious how it's maintained. There are two principal obstacles to be overcome. If you squeeze something, first of all, it tends to get hot from adiabatic heating. There's a rapid buildup of an opposing pressure due to the contraction process. Now, it's true, when something contracts, the gravitational, self-gravity gets larger as well, but if you don't get rid of the energy, the pressure builds up faster than the gravity. The pressure buildup will stop the process. The second obstacle to be overcome is the rapid buildup of an opposing centrifugal force due to angular momentum conservation. The same type of process that occurs when a figure skater pulls in her arms, spins faster and faster. And once again, as we contract, the effective centrifugal force associated with that builds up more rapidly than the self-gravitational force. So it must be overcome. Now, in practice, the counterpressure from adiabatic heating is not an insurmountable obstacle to accretion because the gas can radiate relatively easily. The radiation carries off a significant amount of energy. Inelastic collisions between gas particles turn into photons. The photons ultimately escape. Accretion requires cooling. Accretion will be a source of luminosity, something to bear in mind. Now is the centrifugal barrier, which is the interesting bit here. This really is, at least a barrier. Nature works it out. It's a conceptual barrier for the theorist to overcome. It's not relieved by radiative losses. The photons carry off energy, but very little angular momentum. Well, with only residual pressure support and a serious centrifugal barrier, collapse, when it occurs, will proceed along the axis of rotation. So gas in the plane normal to this axis is supported by rotational forces. So that's a description of a process which I think is more intuitive. Here we see a man tossing a pizza. It becomes extended. Essentially, the rotational forces keep the dough extended, and the process of formation requires that the pizza dough rotate, but I think it's not a great leap from that to something more spectacular. So accretion must pass through a disk phase. This is what I'm trying to get at. So we speak of an accretion disk. Accretion disks have acquired a truly iconic status in modern astrophysics. There's a conference on high energy astrophysics. There'll probably be a little picture somewhere, or a big picture, of an accretion disk around a black hole with the jet coming out of it. For many years, we didn't know how the accretion process worked in disks. Disks can be imaged these days. This is a Hubble Space Telescope picture of the center of a galaxy. There's a big dusty torus, which you see in brown, and a little white spot at the center, which is the actual final accretion disk itself. This is a more recent picture from ALMA, which shows the internal structure in a protoplanetary disk. And although you can't quite make it out, I think from the image on the screen, it turns out that there are planets in that picture which are doing secondary accretion from the disk itself. This is the sort of science that will soon be available routinely with this instrument. Okay, so there is abundant observational evidence that disks are hot. It's much easier to record the spectrum of the disk, especially around a compact object, than it is to get a picture of the disk at disk around the black hole is simply still too small to be imaged. Disks are hot, and they're too hot without an energy source. Without an energy source, they should cool down rapidly. But there is a natural source of free energy in the disk, the differential rotation itself. Now, the emissivity quantity, which tells me how much energy is coming out per gram of fluid, is given by a formula. Whoops, got ahead of myself. I have the laser pointer, not quite. It's given by the formula in yellow. So omega here is the angular velocity of the disk locally. D omega dr is the derivative. It tells me how much shear there is in the disk. R is the disk radius. And T is an interesting quantity. T is the proportionality constant here. T is a quantity I'll come to in a minute, which is directly proportional to the angular momentum transport. So you see from this formula, d omega dr is less than 0. So disks rotate faster on the inside than the outside. So minus d omega dr is a positive quantity. If we want energy to be released, making Q positive, this implies that T, the quantity proportional to the angular momentum transport rate, must also be positive. So if disks are both hot and strongly transporting, the picture that emerges is one of turbulent flow. That's what turbulence does. It's highly dissipative, it produces a lot of heat, and under these circumstances, it also enhances the rate at which many quantities, including angular momentum, is transported through the disk. I should say particularly angular momentum in a system where the source of free energy is the shear. Mixing of the fluid elements enhances both dissipation and angular momentum transport. So this focuses the problem. We want to understand what the source of this turbulence is. Disks need to be turbulent to operate. Now we can come back and ask a little bit more, look a little more carefully what this T quantity is. So T is something called a tensor. It's a stress tensor. And you should think of it representing here is it's some kind of an average quantity of the density rho, and then delta Vr and delta V phi are velocity fluctuations in the radial direction and the azimuthal direction. Radial means the direction out from the center. Phi is the direction around the disk. So in order for that quantity T to be positive, when I have a positive delta Vr, I need a positive delta V phi. And if they're both negative, that works as well. So I either transport positive angular momentum outward or negative angular momentum inward. The net result is a net outward transport of angular momentum. Correlated fluctuations like this are at the heart of accretion disk theory. It's not good enough just to get the disk to splash around. That'll make noise. We need to get correlated fluctuations. When I have a positive outward little blip in my velocity, it has to be associated with a positive delta V phi. So what makes a disk turbulent? That's the big question. And it's interesting now to go back and look at the history of modern accretion disk theory. It received its real impetus from the search for black holes, which began in the 1960s. The important idea is, of course, you don't see the black hole itself. It's black. No radiation escapes. What you see is its effect on the surroundings. And in particular, in a binary star system, where one of the stars is a black hole, an accretion disk should form. It often forms by matter transfer. The black hole is close enough to its companion star. Matter is transferred from the ordinary star onto the black hole. And the gas itself, by studying the gas as it disappears into the black hole, this reveals indirectly the presence of the embedded central black hole. And if we're lucky, even tells us something about the black hole itself. There's the sort of canonical picture that people have in mind. Big normal star losing mass into a swirling accretion disk disappearing into the black hole. But you have to know how to read the disk. You're going to use the disk as a proxy. You're going to use the disk indirectly to tell you something about the black hole. You'd better understand the physics of the disk. And that's where the problem came in. So a big leap forward occurred in 1973 when a theory of accretion disks was created by Soviet scientists Nikolai Shakura, Rashid Sunyaev, based on the assumption that the disk was turbulent without any specific mechanism for how it got that way. The Shakura-Sunyaev theory is such a good theory in many ways, it's still widely used today, and profitably so. Important predictions of the theory, such as that the surface temperature goes as the -3/4 power of the radius. These turn out to be independent of the modeling details. That's something that arises, it turns out, in any disk where the turbulence is dissipated locally. It doesn't matter the exact nature of the turbulence. This was an important finding of the theory. But other results that you would like to know, the details of what the disk looks like, these were sensitive to the additional assumptions, the auxiliary assumptions that had to be made. The principal one of which was that this stress tensor, this funny thing with these correlated fluctuations, largely on the grounds of dimensional analysis, was arbitrarily set proportional to the gas pressure P. In circumstances where radiation was important, people argued whether you should include radiation pressure or not. We'll leave that aside for the moment. TR phi, the stress tensor, was proportional to P, proportionality constant. It was just a number, alpha, which you didn't know. So these disks were known as alpha disk, and the Shakura-Sunyaev theory is generally known as alpha disk theory. So Kip Thorne, who was one of the leaders in the 1960s and 70s in the hunt for black holes, and made very important contributions to our understanding not just of black holes, but accretion disk theory, put his finger on the problem. In a 1974 article in Scientific American, Kip writes, "The chief stumbling block at this point is the friction in the disk," meaning the turbulence. "We do not know whether the friction is generated by turbulence in the spiraling gas, by magnetic fields in the gas," haven't talked about magnetic fields yet, "or by a combination of turbulence and magnetic fields." So Kip is a very clever guy, and in 1974 he was already thinking along fruitful lines. Indeed, I would say that the answer to his dilemma is yes. Turbulence and magnetic fields, but not quite in the way that he had arranged his thinking in his own mind. They're inextricably entwined. Common wisdom circa 1973 was there's shear in disks. The actual physical viscosity, the microscopic viscosity in disks, the coefficient that arises from particle collisions, the coefficient of dissipation arising from particle collision, is very small. And under laboratory conditions on Earth, in many types of flow, that in and of itself leads to turbulence. Well, the onset of turbulence was, and it certainly remains, a very contentious issue in fluid dynamics. And to this day, there's really no good evidence. In fact, there's compelling counter-evidence that the kind of motion associated with accretion disks, Keplerian motion, where the period is proportional to r to the 3/2. Law obeyed by the planet is also obeyed by the gas in the disk. The pressure support is small. For that kind of a flow, shear itself is not enough to bring on the onset of turbulence. So the idea, or the problem, is due to this man, Mr. John Strutt, 3rd Baron Rayleigh, known more widely as Lord Rayleigh, and the Rayleigh criterion that he came up with in 1916. I don't know whether it was published then or whether he thought of this earlier, but he has a very nice argument. So we consider two rings of material, equal mass, in a disk, and I want to interchange the rings while conserving my angular momentum. So I bring R2 down to R1 and push R1 out to R2, conserve my angular momentum. I compute the energy before, or how shall I say, I compute the energy after, and then I subtract the energy before, and then I see whether the energy has gone up or down by that process. If the interchange lowers the energy, it's unstable. If the interchange raises the energy, to speak now of kinetic energy of rotation, then the interchange is unstable. It's a very easy calculation to do. I won't go through the details, they're easy enough to work out. But the bottom line can be stated rather simply and elegantly, and that is, if in the disk the angular momentum per unit mass increases outwards, you have more angular momentum per unit mass in the disk in the outer regions, then you are stable. And the problem is that just about any accretion disk that you're interested in studying has this kind of rotation law. And in fact, it is true for galactic disks, and it's true for Keplerian disks, and it's a big problem. So let's look at the details now. I'm going to write down some equations. So I just am setting up my coordinates here. X and Y are coordinates in the radial and the angular direction that travel around in a circle with my unperturbed gas. The idea is I'm going to push on the gas and make a little excursion in X and Y, and then I ask myself, what happens to the gas when I disturb it like this? This is a simple problem. The equations of motion look like this. X double dot represents the acceleration in the x radial direction. The 2 omega terms, minus 2 omega and plus 2 omega, you recognize as the Coriolis forces. And then there's an additional term, which is essentially the centrifugal term, and it comes in the form of a derivative because it's really the difference between the centrifugal term and the other forces that are present holding the disk together. It's proportional to d omega squared d log r. System of two very simple equations. We can look for solutions of the form e to the I omega t, and you find that such solutions exist if omega is equal to this expression on the right, which is essentially just the derivative of the square of the angular momentum. So it's a reproduction of the Rayleigh conclusion that I get oscillating stable solutions if the angular momentum increases outward. This quantity arises often, it's given a special name, the epicyclic frequency, we'll see why in just a moment, and it's denoted as kappa squared. So, the actual deviations look like what I have printed on this slide. Y is proportional to, or equal, let's say, equal to cosine kappa t for a unit displacement. And x is minus kappa 2 omega sine kappa t. And what that does is give you an orbit like you see in label B here. This is now, remember, in a frame moving with the disk, and the excursion proceeds in a retrograde sense. These are epicyclic motions known as epicycles. V represents a stable displacement. That's the solution to the equation. What we would like is an unstable displacement, something like A. these equations are not going to give us trajectories that look like trajectory A. The Rayleigh stability criterion is comfortably satisfied by Keplerian galactic disks. We should expect to see epicycles, but no breakdown into turbulence. The latest word experimentally, this is actually a nice paper from 2006. There are more recent results to be published, but I think the title says it all. Hydrodynamic turbulence cannot transport angular momentum effectively in astrophysical disks. In the laboratory, they're able to look at water experiments with Reynolds numbers. In this paper, up to 1 million, more recently up to 10 million, and profiles that mimic a Keplerian profile are as stable as the experimental apparatus can measure essentially no difference between uniform rotation and Keplerian rotation in the level of noise that they see. And they have tried mightily to make this apparatus go unstable. For those of you who are familiar with the term, this is a Couette flow apparatus measuring the flow between two concentric cylinders. But it is a remarkable fact, and this is why we're here today, that if there is any electrical current flowing in the fluid, the dynamical stability, F equals ma stability, these properties are dramatically altered. The system is destabilized. Not if the angular momentum increases or is faster on the outside. Excuse me. Say it again, I'm getting myself confused. It is unstable, not if the angular momentum decreases outward, but if the angular velocity decreases outward. And it's much easier, much more common. It's the general rule that the angular velocity will decrease outward rather than the angular momentum. The instability at work, which I'll describe here, is of course known as the magnetorotational instability. So this is what John and I elucidated back in 1991. It had precursors, interestingly enough, in the laboratory fluids community, Velikov and Chandrasekhar in 59 and 60, who sort of began an investigation, found essentially the analog of this instability, but it wasn't understood. They were analyzing it in its global form, and it's a very local instability. So the significance of what they had was totally lost for 30 years. So to understand why the magnetorotational instability works, we make use of a couple of classic results of the Swedish physicist Hans Alfvén, who won a Nobel Prize for investigating the wave-like properties of magnetized media, which are not rotating. And John and I essentially investigated the same type of problem with the addition of rotation, and then that turned out to be extremely fruitful as well. So looking at how waves behave in magnetized medium has been a very fruitful exercise in theoretical astrophysics. So the work of Hans Alfvén showed that if one wants to look at the behavior of a magnetic field in a gas, which is a good conductor, and astrophysical gases in general are excellent conductors. Under these conditions, if I look at what the requirements of the Maxwell equation, particularly the induction equation, tells me, and I combine that with the statement that the Lorentz force on the charges in the fluid has to vanish, one finds that the magnetic field in the conducting gas behaves as though it moved with the gas, that it is frozen in. Bending a magnetic field line by shearing motion of the gas creates a return tension force, like a plucked string, or like masses on springs. And in fact, masses on springs is a very good analogy to use, and that will help us understand the magnetorotational instability. In effect, the magnetic field in a magnetized medium results in forces between fluid elements that are almost exactly analogous to two masses hooked by a spring following Hooke's law. I always find that remarkable. Magnetic gas, it could have been a mess. You have protons, you have electrons, protons are doing proton things, electrons react differently, you get different currents, the currents make magnetic fields, the magnetic fields then induct back on the charges, makes them move around again, gives different magnetic. That could have been an intractable mess. But no, it's actually very simple. The magnetic field lines of force simply behave as though they're frozen in the gas, and they behave as though they were a simple tension force. Waves move along the field line, literally like a wave along a string at a velocity given by the magnetic field divided by mu naught perhaps, mu times rho. Mu naught, or mu is my mu graph permittivity of free space. That's the alphane velocity, rho is the density. So let's go back to those masses on springs and consider two masses connected by a spring in orbit about a star. This is really what's going to happen with fluid elements that are threaded by a magnetic field. So we zero in on the small scale picture, and I have two masses connected by a spring. Omega 1 is the angular velocity of the inner mass. It's going a little bit faster. Omega 2, the angular velocity of the outer mass, going a little bit slower. So you can see the inner mass is going to pull ahead a little bit, but that magnetic spring force will pull back on it. It will tend to retard its motion. That creates torque. It loses a little bit of angular momentum. It doesn't have enough angular momentum to stay in its orbit. It drops down. Exactly the reverse happens with the upper mass. It acquires the angular momentum lost by the inner one. It now has too much angular momentum to stay in its original orbit, and it moves outward. The string, or the spring, stretches yet more. The torques go up, the process returns, and we have a runaway. This is the magnetorotational instability. It's really, in its essence, very simple. The actual equations of motion, when I look at them in detail with the spring present, look exactly like the equations that I did before, except for this k. This k term simply adds to the centrifugal term. And most critically, in the y equation of motion, where there used to be sort of a zero, there was nothing proportional to ky, so you notice those two terms are an exact derivative. You can integrate that equation. Y dot plus 2 omega x is a constant. That's conservation of angular momentum. When I put in that ky, that's what causes all the trouble. Angular momentum is not conserved in an individual particle now. It's the torque. And so when I look for wave-like solutions to this system of equation, I get something astonishingly more complicated, at least mathematically. And in particular, you see the appearance of d omega squared dr apart from the epicyclic frequency, kappa squared. Before that, d omega squared dr term appeared embedded within the kappa squared term, turning it into an angular momentum gradient. Now d omega squared dr appears by itself. And if you're good at math, and you think of the limit that k goes to 0, and you can see pretty quickly from the form of this equation that d omega squared dr is less than 0, you'll have omega squared less than 0 solutions, i.e. omega is imaginary, corresponding to instability. Amazingly enough, as I say, moving to the magnetic field equations, not just the mechanical equations, introduces absolutely no further complications. Here's the physical picture. Here's my disk, a magnetic field threading it. Disk going around. I make little perturbations in the magnetic field in the z direction, as you see. I write down the equations of motion now with the Lorentz J cross B force. It looks exactly like the equations. This is not artist's conception of the equations. These are the equations. They really are. You just replace k by kVA. This little k, by the way, is the wave number of the disturbance. VA is the alphane velocity that we saw before. And there's the dispersion relation that results. And once you have the dispersion relation, the solution for omega, in very short order, you can show that if d omega squared dr is less than 0, you have instability, and the disk does this, at least in linear theory. If I compare the MRI criterion for instability, you can see directly d omega squared d log r. The log you can forget. Just consider d omega squared dr bigger than 0 is the stability requirement for the MRI versus dr fourth omega squared dr bigger than 0, which is the Rayleigh criterion. That r to the fourth is an enormous factor. It makes it much more easy to satisfy. So the presence of a weak magnetic field, you see why a weak magnetic field still works? Because the magnetic field appears only in the combination kVA. So if I scrunch up the magnetic field on small scales, making a big tension force, if I have any VA whatsoever, I just choose a K big enough so that kVA, which is the important complication, that term can always be made significant. The presence of the weak magnetic field allows the free energy gradient to be a stability discriminant, to determine the stability of the system. Shear is a source of free energy, and shear also, the sign of the shear also determines whether I have instability or not. My stress tensor, when I go back to that, I have to include velocity fluctuations and fluctuations in the magnetic field as well. The same story holds, the same basic ideas there. I'm going to show one video, leave the real fireworks to John. These are the effective equipotentials on a disk. They have this funny teardrop shape. This is because of the rotation. The equipotential surfaces of constant potential energy, the surfaces in motion would assume if it was just standing by itself. This is where surfaces of water would fill up. It gets quite distorted because the disk is dominated by the rotational potential. And bear that in mind as we look at John Hawley's bicycle tire simulation, as he fondly calls it. We're looking at an initially stable configuration without the magnetic field loops embedded in the disk, and this is what the magnetorotational instability does to a disk when you get past the linear approximation. This was sort of where I got off the bus. I could do the linear stability analysis. Fine, thank you very much. But we needed a computational expert to understand what really happened after that. And this is where John's work was absolutely indispensable. Let me just briefly, because I don't have much time, I'm not sure how I'm doing, but it's probably time to wrap up my portion of this. I want to talk about what I call the insidious effects of weak magnetic fields. Here's a thought experiment. Is there an entropy analog of the MRI? The MRI connects two masses and causes a flow of angular momentum between them. Can I imagine a system in which entropy might do the same thing? There's the MRI. Here's a proposed magnetothermal instability. Two blobs, two different temperatures, T1 and T2, somehow entropy, heat, think of it as heat, flows from T1 to T2. T1 loses energy, gets denser, sinks, gets buoyantly heavier, it sinks. T2 heats up, rises. Now, if somehow the process of separating should increase the flow of heat between them, I would have conceptually the same ingredients I would have to make a magnetorotational instability. The problem is, it seems, why should that happen? Why should I get an increased flow of heat when I separate the elements? Well, it turns out this thought experiment can be realized in nature because heat is conducted by electrons only along magnetic lines of force. The electrons in very, very tight orbits around the magnetic field, and it doesn't allow any collisions to go perpendicular to the field lines. The collisional transport of energy travels only along the field lines. So this really does happen in the dilute plasma. Here you see field lines on the bottom. I have two fluid elements. I'm hot on the bottom, I'm cold on the top. I bend my field lines. Heat starts to flow from the hot gas to the cold gas. The hot gas rises, the cold gas sinks, it drags the field lines with them, and I get more and more heat being transported because I have a bigger component of the magnetic field line along the temperature gradient. This turns out to be an important process that goes on in clusters of galaxies. And it turns out, I'll have to stop here because once you get me started talking about my work, it's very difficult to turn off. But this is only the beginning. There are many, many other thermal analogs of weak magnetic field instabilities, which are only now being explored. So the MRI has led us not only to an understanding of accretion disks, but many other properties of plasmas as well. The overarching principle is that weak magnetic fields profoundly influence astrophysical gas dynamics. The MRI is but one of several manifestations of this behavior. One of its most important consequences is that we can understand accretion disks as a result of understanding what weak magnetic fields do. But many types of systems are affected. The widespread implications of weak magnetic fields are only beginning to be understood. What does seem certain is that astrophysical gases are much more prone to instability and turbulence than was naively thought before people started to think along these lines. Weak magnetic fields essentially tap into free energy gradients, making them a source of instability. There are many astrophysical plasmas that appears to require, as yet, elusive energy sources. People who know about cooling flows in clusters of galaxies is a prime example. Gas should be much cooler than it is. It should have thermally collapsed a long time ago. There's somewhere unaccounted for heating sources. There is great promise, I think, for elucidating. That's a wishy-washy word. Solving many of these mysteries. Cluster cooling flows, the hot interstellar medium, gamma ray bursts, just to name a few. And, as my title suggests, even beyond that. And I will stop there. Thank you very much.
Telling us the importance of magnetic fields in influencing the daily gas dynamics of accretion disks. Now it's my pleasure to introduce our second speaker, who is the winner of this year's Shaw Prize in Astronomy. Professor John Hurley is currently the Associate Dean of the Sciences and Winner Professor of the Department of Astronomy at the University of Virginia. He obtained his PhD from the University of Illinois in 1984 and was Benjamin Fellow at the California Institute of Technology from 84 to 87. He has been with the University of Virginia from 1987, going through the ranks from assistant professor to professor. His activity, as you have heard a little bit from the first talk, has to do with computational simulations. As you know, that one of the great advantages that we have gained in the last couple of decades is our ability to go beyond simple mathematical calculators on pencil and paper to the time that we can perform and calculate the complex behavior of dynamical processes by using sophisticated modern computing facilities. And the part of the challenge has been not only in terms of making use of the hardware, but also developing efficient and accurate algorithms in doing these physical calculations. So I would now want to invite Mr. John Hawley to tell us about his part in solving the mystery of these rotating accretion disks. Mr. Hawley.
Thank you very much. In particular, I'd like to thank Steve for that nice introduction to my talk, having set up the problem so that you can now hear what's really going on. The title of my talk, Exponential Growth, the MRI, and the Development of Accretion Disk Simulations. The term exponential growth here refers to two distinct things. One, a linear instability like the magnetorotational instability. The perturbations grow at an exponential rate. That's what makes them very interesting and powerful. The other exponential growth that I'm referring to here is the exponential growth in computing power that took place over the last several decades. And the thesis of this talk is that our understanding of accretion disks has been mediated by two important factors. One that Steve has described, the fact that we simply didn't know what caused the turbulence within the accretion disk. The second was the lack of computing power in order to solve the equations. All right, so the universe is, as Steve said, full of structure, and it was a universe that starts out remarkably smooth. In the Big Bang, and this is a picture from the Planck satellite of the microwave background temperature, and just look at that and say, oh, well, there's lots of structure there, lots of little fluctuations, except that these are temperature differences that are on order of 1 in 100,000. So really the universe was very, very smooth. And if that's all that was going on, in fact, there are bigger perturbations in so-called dark matter, but this isn't the cosmology talk. The point is that the universe is full of structure today, and so where does that structure come from? Structure in the universe comes from gravity. Those perturbations start as fluctuations in the cold dark matter and in the density of the gas, and gravity pulls that matter together, and as matter becomes more and more dense, the gravity increases, forming more and more structure in the universe. So there's structure on all scales. There's huge structures that cover megaparsecs in size, the great filaments, down to the galaxies themselves. And then once you get into the galaxies, you can go all the way down to stars. Stars are an example of an amount of gas that's been drawn together by gravity. It's been drawn into a spherical shape. And the interesting thing about stars is that they're actually very, very simple objects. First, they're basically spheres, which means you can describe them in terms of simply functions or density, temperature, and such that is only a function of the distance from the center. The very center of the star is the hottest, densest place. The outer region is cooler, less dense. The star doesn't change its size. It's stable. The sun's been sitting there burning in space for 5 billion years. It's changed a bit over time, but it doesn't change rapidly. So it's in a state of equilibrium. So you have a set of equations that depend only on the radius and don't depend on the time, and simply represent two things: a balance of internal forces and a balance of energy. That is, energy is released in the center of the star from nuclear reactions and is radiated out into space at the surface of the star, and the energy generation rate equals the radiation rate. So everything's in nice balance. When you do all that, you end up with a nice set of simple, relatively simple equations. Okay. Now, add one tiny additional ingredient, a little bit of spin in the gas, and you get not a spherical star, but a disk. And so disks, as Steve said, disks are all ubiquitous. They're disk things throughout the universe. A galaxy, disk-type galaxy, a protostar forming a disk, and a binary system where a ordinary star is close enough to some compact star that it actually transfers matter from the star to the other star, and in doing so, that if there's too much spin, and it goes into orbit around the compact star, forming a disk. Okay, so if we, for example, consider the binary star system We have here one of those nice animations that NASA produces to explain why it's important to give them lots and lots of money, showing basically what it looks like in a binary star system with a giant massive star transferring material from the star into a disk around a compact black hole. Up there you see the hot spot where the flow from the star impacts the disk. It goes into orbit. By some process, it slowly spirals in, as it does basically matter falling in a gravitational field. As you drop something in a gravitational field, it picks up speed, and if it smacks on the floor, it will release that kinetic energy of motion as heat. It radiates the heat, so as you go from the outer part to the inner part, the gas gets hotter and hotter and hotter, radiating light, and thus that's what you can see in the X-ray satellites that NASA and the European Space Agency launch. All right. Now, when I talked about the star, I said you could describe the star with a set of very simple equations, simple ordinary differential equations, the kind of math that you learned from your mother when she would, you were 5 or 6, and she would read to you mathematics texts before going to bed at night. So those simple equations. When you go to a system that's like an accretion disk, first off, it's not only dependent on the radius from the central object. It's not, it's in a disk. So this part up here away from the disk is quite different from in the disk. So it's at least 2 dimensions. And in fact, if there's anything going on around the orbit, it's full 3 dimensions. Okay, so you really need 3-dimensional equations. Another thing is that it's not time independent. It varies with time and varies rapidly. You've got gas orbiting near the speed of light close to the black hole, and it's quite different orbital rates from out here, and if the gas is fluctuating, turbulent, it can be quite a mess. It might be, on average, sort of time independent, but the equations themselves are going to be time dependent. Okay, so you've got some set of equations. You don't need to solve these. These won't be on the exam. Whenever I show something like this to my students, I always say, no, just relax. We're not going to do anything with these, just so I have something to gesture to. You've got a set of complicated equations, differential equations, partial differential equations that depend on multiple dimensions and on time. And so it's very difficult to get a solution for this using traditional paper and pencil. And so it comes in, the idea then is, why not use the computer? Let's solve these equations with the computer. Okay, now, again, going back to the star. People had solutions for star-like objects over 100 years ago, well before the work on nuclear reactions that actually showed us what it is that powers stars. I mean, the existence of stars was well known many years ago. The ancients actually were aware of the existence of the sun. So they knew that there was a source of energy, but what it was a little uncertain. And eventually people figured it out, but you didn't even need to know what the source of energy was in order to describe the structure of the star fairly accurately. You just needed to know there was one. And once you had the nuclear reactions, then you could tie that in detail to the energy generation rate inside the star. You could relate that to the mass of the star. And then you could follow different types of stars at different points in their ages. And you could explain this. This is a Hertzsprung-Russell diagram of stars, an empirical observational finding that stars don't exist. The vertical axis is the star's luminosity, and the horizontal axis is temperature. And what one sees is that stars are only found in certain locations as a function of luminosity versus temperature. Okay, so the so-called main sequence lies along here, and these are the sort of stars like the sun. And the sun list is, see down around here, it's one solar mass. As you go up to higher mass stars, they're more and more luminous and much hotter on the surface. Down here you get the red dwarfs, which are smaller mass, lower temperature. And you find that other types of stars, late in life stars, end up here, and then they kind of go up here on the so-called asymptotic giant branch. And so this was known empirically. And one of the triumphs of early computation was that stellar models could explain why the stars were in these positions and could explain how the stars moved from one spot to another over their billions-year lifetimes. Okay, so the theoretical explanation of the Hertzsprung-Russell diagram and stellar structure, stellar modeling, stellar evolution was a triumph of early modeling, computational modeling. Okay, so this was sort of all kind of wrapped up by the 70s, and I learned about it in my undergraduate course on stellar modeling. It was great, wow, you use computers, figure it all out. Isn't that really neat? So, well, we did stars. Let's go to the next system up, disks. Should be simple. The idea, let's consider black hole. Let's let the equations tell us what's going on. So, imagine a certain amount of mass, an angular momentum coming in towards the black hole, and at the other end, coming out is the light from the disk. It may be a jet. It's jet optional. Not all systems have jets, but if we give the equations to tell us what's going on, we'll know when there's a jet. So this is the black box that's solving the equations for us. So we have our inputs and we get the outputs, and they match up nicely with everything we observe in disk systems in the universe, and our job is done. Right, straightforward. The trouble, of course, is that it's not that easy. Okay, and let me just give a sort of a quick idea of the sort of the numerical approach that one takes to solving those equations on a computer. First off, the computer has to work with discrete elements, and so you divide space up into zones, which represent here a set collection of grid zones, individual boxes that represent some finite amount of space. And inside that, you say there's a certain amount of gas, certain gas density, and that gas has a certain temperature. It maybe has a certain momentum, velocity, and that's the smallest unit that you've got. That is, that you can't really describe any substructure here. Okay, so you break up space into discrete cells, discrete grid zones. You convert the continuous variables of density, temperature, pressure, all these things into discrete values associated with each zone. Then you take those equations and you take the continuum differential equations and change them into finite difference equations. Okay. So you represent then the laws of physics in terms of finite numerical differences, which is an approximation, right? But it's an approximation that in the limit that these little cells go to tiny, tiny size that approaches the actual mathematical approaches the mathematics at a rate that at least is as this delta x, the size of the thing, goes to 0, it approaches it exactly. At least there's some best systems that approaches it faster than that. But in any case, now this is where I started. All right. Mid-70s. This is how people did stellar modeling. Punch cards. Okay, and notice up here, I really like this. Fortran statement. Okay. We're still programming Fortran, by the way. We don't use punch cards anymore. And the latest versions of Fortran don't require that you only use 72 characters. That's not free format, but it's still called Fortran. So, this is where we were. The computers at the time were very slow compared to what we have today. Reading these cards in was actually very slow. You put them in the machine and it goes thump, 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 thump. So, the program was a big stack of cards like this. And I remember one night I put the big stack of cards into the card reader, and it went thump, thump, thump. I said, what's going on? And I said, my cards are coming out in a different bin. They normally come out in this bin over here, but now they're coming out in this bin. That's the night I discovered that in addition to being a card reader, the machine was also a card puncher. And somebody had left an active punch job that had run out of raw cards to work on. And so it overpunched my deck with something else, thereby rendering my deck completely useless. So I had to repunch the entire program on the cold key punch. It's a good learning experience. It gave me a story I could use 35 years later. Anyway, the need for speed. It's actually pretty easy to figure out what you need to do these sort of calculations. The unit of measure is a floating point operation. How long does it take to do one number times another number, or one number plus another number? It actually takes a large number of floating point operations to do a division, but let's not worry about that. Well, you're going to have so many grid zones. And you're going to have, say, 100 grid zones in one dimension. If you have 2 dimensions, and you also have 100 grid zones, okay, so that's 100 by 100, or 10 to the 4, 10,000 grid zones. So number of zones per dimension to the nth dimension, times the number of time steps you need to advance the problem forward in time, times the number of floating point operations you need to update one grid zone. So, okay, an example then, 2-dimensional hydrodynamics on a 100 by 100 grid, which is, it's a pretty crude grid by these standards today, and you want to run it for 10,000 time steps. That's pretty short by today's standards. And it takes a simple algorithm, takes about 1,000 floating point operations to update one grid zone. The whole calculation then requires 10 to the 11 operations. Okay. Well, you'd like to have it done in an hour or two. Back in those days, you shared the computer with everybody else, so you didn't get very many hours to use it. The point is that, let's say you want to get it done in an hour or two, that's going to be about 10 to the 3 seconds. So you really need a machine that can do 10 to the 8 or 100 megaflops, 100 million floating point operations per second, okay, to do a 2D hydrodynamic problem of that complexity, which is, again, not very much. 3D MHD, again, 3D requires 100 to the 3rd if you're doing 100 by 100 by 100. You need to run longer, as it turns out, and the complexity of the equations goes up, and then you're about 10 to the 15. Okay, so if you needed 100 megaflops for this one, you need a factor of 10 to the 4 more, which is a gigaflop, 100, a teraflop. Okay, if you want it done in a couple of hours. If you're willing to wait for several days, let it run for several days, you can bring that down by an order of magnitude, which you can do. Okay, so aspirational. Well, let's try to get it up to 1,000 cubed grid. Run for 1 million time steps and add some more physics, say radiation transport, which will increase it by another order of magnitude. So that's 10 to the 20 floating point operations. Now we're beginning to talk real money. Right. So here is a plot showing computing power in terms of floating point operations per second from the early years up to 2010. Back in these days, things were really quite slow, but it was still an important step forward. And so that's 10 to the 8. Right? That's what I said you needed to have to do 2D simulations. Notice that basically 10 to the 8 comes in sort of around 1980 or so. Okay, and that was the introduction of the Cray 1 supercomputer. This Cray 1 here is the Cray 1 that was at Max Planck Institute for Astrophysics at Garching by München in the 80s. And this is the first Cray 1 that I used. And it is now preserved, because I used it, it is now preserved at the Deutsches Museum in Munich. So next time you go by, say hi to it for me. Now, I said we needed another factor of 10 to the 4 to do 3D, but yeah, I said if you were willing to run longer, you could bring that down to maybe 10 to the 3. So that's where we got a need for 3D. And you'll notice that basically in sort of the late 1990s, mid 1990s. Okay, so keep that in mind. Now, the early accretion simulations. Here is a little known fact. James Wilson, who was the scientist at Lawrence Livermore National Lab, wrote a paper that appeared in a conference proceeding in 1975 entitled Magnetohydrodynamics Near a Black Hole, where he had written an MHD code in full general relativity. He'd run a simulation of inflowing gas with magnetic fields in an accretion system. The trouble was, he did it on a grid of 20 by 30 zones. And that was not enough to see much of anything, really. He was hoping to see that the magnetic fields could provide a connection between a rotating black hole and the surrounding gas. And there was some evidence of that, yes, that he could transfer energy from the rotation of the black hole to the surrounding gas. So he was able to show that. But beyond that, not much. But that was the right idea. Okay, and if he, 30 years later, with more computing power, it would have been something. But I worked with Wilson and Larry Smart in my PhD thesis, and we decided to simplify things by getting rid of the magnetic field, which would reduce the complexity of the problem, by about an order of magnitude. And just consider in 2D the case of gas falling in that's rotating somewhat, but it's not actually in a disk. It's just falling in and rotating. And this is a lurid photo of what results in this dark red stuff is a forming hot torus of gas surrounding the black hole. I would also point out that this was circa 1983-84. These were sort of the first time that we were doing color images of simulations. Sort of very new back then. A lot of the images I took were actually by mounting a camera on a tripod in front of a CRT screen using film. Okay, so several obsolete technologies there. Film, CRT screens, and SLR cameras. Okay. Now, here's sort of an artist's conception of what we got, which was an orbiting torus of gas, which is now somehow I've referred to as the bicycle tire. And this blue thing here represents the centrifugal barrier. Steve mentioned the centrifugal barrier in his talk. That is the point, because of the angular momentum the gas had, that was the point beyond which it could not go. It was blocked from getting into the black hole. And see, there was no mechanism for the gas to lose any of the angular momentum. So it formed the torus, and then that was kind of it. The torus would simply build up in size, but you couldn't accrete it any further. And so it was right up against the angular momentum transport problem. And all I could say at this point was that whatever the angular momentum transport was, it wasn't in the equations of general relativistic hydrodynamics surrounding a black hole, because there wasn't any transport of angular axisymmetry. So I moved on to Caltech. And at this time, you remember I said that I went to Germany to use the Cray supercomputer in Max Planck. This was because there was no Cray supercomputer available for U.S. researchers in the United States at this time, in the 80s, early 80s. Except the only ones we had were in the national weapons labs, which I was not allowed to use. And so my advisor, Larry Smart, said this was an example of an American scientist going to Germany to use an American-made supercomputer. And on that basis, Larry was able to convince the National Science Foundation that they needed to establish the National Supercomputing Centers. And so they decided, yes, we need to bring supercomputing to American researchers. And it was going to take some time to get those centers started. So the first thing they did was basically spend money to buy time from commercial vendors. And because I was at Caltech, the nearest commercial vendor was located in Culver City, which we'll call Hollywood for the purposes of this talk, which was a place called Digital Productions. Okay, this is a picture of me working at Digital Productions on a simulation of a gas ring. This is the Cray XMP that Digital Productions owned at the time. And this is the movie you might have seen, possibly, that they developed here in the 80s. This actually was the first movie where all the special effects were done in the computer. First, there'd been some computer stuff before, but this was the first time all the special effects were done. The only thing that wasn't done in the computer was the stuff involving actual humans, where they pasted the latex onto the aliens and whatever. And of course that's common today. Nowadays they don't do anything out of the computer, but that was the deal then. So Digital Productions in Hollywood. thing I was working on was something called the Papaloisu-Pringle instability, which had been discovered by Papaloisu and Pringle. And it was that these toruses that I talked about earlier, these bicycle rings, if you looked at the stability property of those toruses from a so-called global point of view, they were unstable. And this was something that my colleagues, which included Peter Goldreich at Caltech, were very interested in. Peter and Ramesh Narayan and Jeremy Goodman had a couple of papers about the Papaloisu-Pringle instability, trying to elucidate it, and I thought, well, that'd be fun. Let's simulate that and see what happens. And this is what happened. It started as a ring, but the ring broke up into these blobs. And this was very cool. And I remember distinctly showing an image like this to Peter and Jeremy and Ramesh and saying, looky, see what happens. The ring breaks up into these blobs. And they look at it and go, I know what's going on there. They ran out of the room. And I finished up what I was doing and went back to the so-called interaction room where the couches and the chalkboard and everything was. And they said, we've got an analytic solution for these blobs. They've solved the blobs in the intervening few minutes that I've been out of the room. And sort of, you could simplify it even further, which I did here. Instead of doing the full ring, let's just isolate on a section of the ring and use Cartesian coordinates and involve it, and then you form the blob. What this actually ends up being is sort of a, if it's orbiting in this direction, it kind of does a counter-rotating epicycle. And you'll remember from Steve's talk, he talked about hydrodynamic stability. If you pushed gas particles, they didn't run away, they just went into a little epicyclic orbit. And so this situation was that there was a readjustment of angular momentum because of interaction between the outer edge of the bicycle tire and the inner edge of the bicycle tire. But it led to reforming the gas into sort of a little vortex, which was basically executing epicyclic motion, and that vortex was sort of in an equilibrium where the centrifugal force was balanced by internal pressure forces. So basically, this is an example of taking this prediction of instability, looking at it on the computer, and coming up with a new equilibrium solution which hadn't been realized before, which then was described analytically. Okay, so this was to me, this was very instructive. It was the synergy between numerical solutions, numerical simulation, and analytic modeling. Okay, now I love this thing. The planet and the Papaloisu-Pringle is so cool, but it's completely irrelevant. Maybe it has a role to play in protoplanetary systems, but it wasn't the solution to the accretion problem. It was an instability, but it wasn't going to solve the accretion disk problem. So I went to Virginia after that, and was motivated at that point to start adding magnetic fields. The reason for adding magnetic fields to the simulations was because at the time we knew that there were jets emerging from active galaxies. Okay, so here is active galaxy Cygnus A in the radio. The galaxy itself is a sort of a little blobby thing that's right down there at the center. And if you look at it in the radio, you see a beam of energetic material flowing out in a bidirectional jet, terminating in a hot spot, and then the effluent from the beam just radiating synchrotron radiation here at the two radio lobes. Now, for scale, this is the size of the Milky Way on the same scale. So these radio lobes are huge structures, and the total energy in some of the biggest ones is huge. And it was realized fairly early on that the only way you could get enough energy to power these jets would have to come from black hole systems, who have efficiencies of converting matter into energy that is much, much greater than nuclear reactions. And it was further realized that the only way that you could really accelerate these jets up to close to the speed of light and keep them collimated was basically by the same sort of processes you would find in a particle accelerator, in other words, using magnetic fields. So the sort of the picture one had, in this artist's rendition here, is of a magnetic field connected to the disk rotating, either the black hole rotating at the center or the disk itself rotating. So a combination of magnetic field and rotation driving the jet outward. So if you wanted to understand jets, you had to add magnetic fields to your equations. All right, now, so that was my goal. That was why I was working on adding magnetic fields. Now, at the same time, I was also looking around for someone who could do analytic stuff, since that had worked out so nicely at Caltech, to have people who could do analytic stuff to help out with the numericals, understanding the numerical simulations. And I found Steve. I said, good. I'll use him. He may not be a Goldbright, Goodman, and Orion, but still seems to have some talent in this area. And so we decided, we're going to study the accretion problem. We're going to consider magnetic fields and with an eye towards getting to where we can do these winds and jets that are powered by magnetic fields. Somewhere along the line, there was this paper that looked at some properties of magnetic fields, and Steve said, I can do better than this. Let me go back to my office and work on this. So I let him go back to his office and work on this. A week later, I took a vacation actually. A week later, I come back and he says, something funny. If you had a magnetic field, it's unstable. And I said, really? Yeah, sure. But if true, that would be very important. But let me see if that's true. So I went back to my office, and using the techniques I've been working on, I did a little problem where I looked at a little isolated section of magnetic field in a differentially rotating system that was rotating like a disk, but it wasn't actually really a disk, it was a box. But it had the properties of a disk. Put in a little weak magnetic field, ran the simulation, which meant I would submit it to the computer that was at the National Center and wait till it ran, which would be an hour or something. He comes back and I see something like this, Say, ooh, that's promising. Run it a little farther and it gets bigger. And so somewhere along the line, I took a print down to Steve and I said, I think you're right. It's unstable. So that was kind of a moment of great excitement. And here is a image from one of the first MRI simulations. Again, just rendering it in color, where this colors are perturbations in angular momentum. So if it's dark color red, that means it's gotten a lot of additional angular momentum. The blue is lost in angular momentum. And so this was a sort of visualization of the process of transfer of angular momentum. And again, it was, I put the image up on the TV screen, mounted the tripod in front of it, took the picture on film, took the film to the 24-hour developers, and got the image back and gave it to Steve, and he put it on his wall. And he still has it, I believe. All right, so, as I said, the need for speed. We're now at 1991 or 1990, which is now at this end of the graph. This plot here shows the history of the top 500 supercomputer. The red is the most powerful computer at the time, at any given time, in terms of measurements of the number of floating point operations per second. The yellow line is the number 500. Now, typically, an astrophysicist doesn't have access to this. It has access more to something like this one down here. And so, this is in terms of gigaflops. I kind of said that you needed to get above 1 gigaflop if you're going to have any chance of doing 3 dimensions. And so you see that it really becomes possible down at the, for the astrophysicists, maybe around the mid-90s. Okay. And you'll also notice that this is an exponential. This is a log plot. It's an exponential growth. And so, it's a factor of 10 here in just a few years, and it just keeps going. And so as you go along, more and more capability comes into play. So the first three-dimensional simulations that we could do, we did it by going to something called the shearing box system, which was to make a local representation of the disk, reduce it down to a small box that might have been cut out of the center of the disk, and it has the differential rotation in that. And in order to have a boundary for this, we just make the top and the end box periodic. But this guy had to be so-called shearing periodic, which is, we imagined an infinite number of boxes just like this one, each sliding past each other at a fixed shear rate. And so we were able to reduce the full global problem down to something manageable. And I think the first 3D simulations we did was something like 30 by 30 by 70 grid zones or something like that, which was what we could do at the time. And this is representative of an early simulation of the shearing box. Oops. Oh well. Trying to get my movie to play here. Okay. So, this is a more recent shearing box. Shearing boxes are still used today because you can now do shearing boxes at high resolution. I think the highest now has been something like 1,000 by 1,000 by 500 zones. You can add more physics. So the shearing box has been done for non-ideal magnetic fields with resistivity, with viscosity, with radiation transport, much more complicated problem. So the shearing box today remains a valuable tool in understanding what's going on in accretion disks. And the number of shearing box papers and the number of people working in shearing box simulations at this point is huge for astrophysics. Maybe 10 people working on it or something like that. Huge number. All right. So you can see the turbulence here. This was basically the purpose of our early shearing boxes, was simply to see the MRI would lead to turbulence within the box. Okay. Now, the real goal, of course, was to simulate the whole accretion disk, not just this small box. And so that's going to take even more grid zones, which is why, the shearing box was done sort of around 95, and we had to wait for another couple of orders of magnitude in computing power. And the big change here was the development of parallel systems, okay? Because the speed of an individual CPU is basically maxed out. It's a gigaflop, and it doesn't get any bigger than that. So the way you get more computational power is to link together lots and lots of CPUs. And so by the by the year 2000, you could have maybe 256 CPUs working together in a single process, a single big computer. And so it became possible to do the full global model. And this is an example of putting in one of those inner tubes and just put some magnetic field, weak magnetic field into this inner tube here in this region, and then let her go. And what one sees is the MRI begins to, the magnetic field begin to go like this, stretch out, make the disk begin to be turbulent, angular momentum is transported, and it starts to accrete and fills in down towards the black hole, which is this little black thing there. This is a representation of density in the gas. And so one transitions from the bicycle tube to this, which is basically a Keplerian thin disk, which continues to accrete as the magnetic field continues to operate, continues with the turbulence. Here's another view, viewed from above, again in gas density, and this sort of shows how the yellow is kind of the dense part near the equator, and the stuff around here is the lighter stuff that's been lofted up above the disk. And you can sort of see some structures here that kind of relate to sort of magnetic fields swinging around. So it has a tendency to cause material to be lost from the disk itself and lofted into the surrounding sort of magnetized atmosphere. Now, the funny thing about this simulation, we were always, in the early days, always visualizing the density, seeing where the gas density was going. And it wasn't until continuing to sort of visualize these things, tried looking at where the magnetic field was going, and something interesting had developed, which was that the magnetic field that was initially put into the disk was carried down by the accretion and deposited on the black hole. And when it did so, matter would drain off the field into the black hole, and the field would actually grow, sort of buoyantly go up the axis. And then so you would have a field that was sort of going up like this with the black hole embedded in the center, right up the axis, which was exactly the configuration one needed to get jets. And so that just happened naturally as a result of the kind of magnetic field that was put into the torus that was carried down to the black hole. And again, it sort of took a while to realize, that actually we discovered jets, how to get jets to work. And the the thing then was to do a visualization showing the jets, and so I'm going to show you a movie of not density, but of magnetic field energy transport, which is, in the case of the jet with magnetic fields, what's happening is the black hole is rotating, and the magnetic field is connected to the black hole, and that rotation causes the magnetic field to basically to propagate a pointing flux or a magnetic energy flux out along the magnetic field lines. And this visualization then comes from data that was taken from one of my simulations sometime in the first half of the 21st century so far. I don't remember the exact year. I gave the data to Andrew Hamilton, who's at the University of Colorado. Andrew was interested in visualizing things near black holes, and he worked out a photon ray tracing technique that would actually use the gravity of a black hole and trace the light motion through the strong gravity of a black hole. And if you're familiar with black holes, you know that their gravity is so strong as to actually bend the light beam. So he was interested in what things would really look like near a black hole. So he was happy to take the simulation and see what it would really look like in a black hole if magnetic pointing flux actually was actually equivalent to yellow light. So that's the simulation. Okay. So you can see the black hole down the center. This is at the beginning when the magnetic field is brought in, and you can begin to see the jet forming here. This stuff here, a lot of that is the atmosphere surrounding the disk. Andrew likes to move the camera angle, fly around the black hole, rather than just sit there statically looking at it from one particular angle. But the point is, here's the jet. And it's formed naturally and nicely, and it does exactly what you want. It produces a bidirectional energy outflow whose strength basically depends on the strength of the magnetic field deposited and the rate at which the black hole is rotating. The process was actually known, it had been predicted in an important paper by Roger Blanford, and Blanford's Nyack mechanism is what it's known as. And it's a way that a magnetic field can extract rotational energy of a black hole. And so as that energy is carried out, it carries some of the angular momentum of the black hole itself. The black hole slows down a tiny, tiny bit. But the energy of a billion solar mass black hole spinning close to the speed of light is enormous. And so that alone could account for the total energy needed to power a radio jet. So, in more recent work, we tried to begin the process of connecting these global simulations to observable properties. And so, one of the first things we did, we couldn't quite do full radiation transport, that is, the radiation coupled dynamically to the fluid as it would be in a real black hole accretion disk, but we could do things like put in, just say the gas is radiating according to sort of a, proportional to the temperature, and that the photons thus produced, the light thus produced, just moves through the gas without interacting with it, and so that's called optically thin emission. That is, the gas is not thick enough to block the light. And so this was a picture of a disk, that what it would look like from the simulation. This, just for laughs here, this ring here is a so-called Einstein ring, which is a point behind the black hole where it emits light, but then the black hole bends the light and forms basically a ring on the other side. So, and this distortion here is also due to the gravity of the black hole, which is you can actually see the disk better behind the black hole than in front, because the black hole bends the light coming from the back into your line of sight. Okay, so that was one example. Here's another sort of thing that we did, which was to look at how the light varied with time and look to see whether there would be any characteristic frequencies associated with that variation. And the answer was not really, but it was a nice try. Work continues. Less by me these days than other people. Lots of people now are doing simulations. There's a lot of codes out there trying to do the global black hole problem. This is from a recent paper, 2013, and they visualized here the disk, a hot disk. There's sort of the hot region close to the black hole. And this is the jet that forms, and they actually run it now out to much larger sizes than the simulations we've done previously, and for longer time intervals, more powerful magnetic fields. And so work progresses, and people are really beginning to get some very interesting simulations, which can be compared to lots of the observations that we have of black hole systems, both in the binary systems and in active galaxies. So, to conclude then, simulations, which started so many years ago, are any day now, we're going to achieve our dream of getting simulations of accretion disks that are like simulations of stars. You just are, more powerful computers and more time, and an understanding of the basic physics that we're doing. So we're learning about accretion disk structures, we're learning about accretion efficiency, variability in these systems, how you can tie that into diagnostics of the spin of the hole, and how we can understand the formation of jets in these systems. But for you young people out there looking to go into astronomy, lots of work is remaining to be done. We don't have a good magnetic turbulence is a difficult problem. It's still difficult even with the highest resolutions. We don't have you have to go from the sort of the little turbulent cells all the way up to the big disk. It's not easy. We've just begun doing things with more precise thermodynamics and radiated transport within the disk. That's very essential because that's the way real disks work. There's a question of how you generate the fields in the first place and whether you can get the large-scale fields needed for jets under general circumstances. And so there's still details of launching mechanisms of jets that need to be worked out. But we now, I think, we're seeing real progress, and we've got the tools, and basically we've got the tools, and we've got the fundamental understanding of what the basic important physical mechanism was, which was the MRI. So I'd like to acknowledge various collaborators over the years who've had roles in this, and of course funding agencies and national supercomputing centers. Thank you.
Thank you, Professor Rayleigh. Please stay. Here comes the question and answer section. May I now please invite Professor Bulbus and Professor Kwok to join us at this session. Please be seated on stage.
Thank you very much for giving us insight not only to the past but also to the future of empirical simulations. I hope that both of you will be willing to take a few questions from the audience. You can ask anything you want.
They can ask anything they want. I'm not going to guarantee the answer.
Right. I mean, I suppose some people are interested only in working itself. Maybe in the history of discovery, anything you would like to ask two short speakers today. Maybe guess not. Okay. I think this is very good. You explain a lot of things. These are fractals and so on. The question that seems to me is that is there any relevancy in our solar system? Perfect. I can understand. Any of the old scheme or which I don't really understand.
Yes, I'll start. And then Steve, correct? The earliest ideas for the formation of the solar system were actually the solar nebular model that became associated with the cloth, but actually went back even further, which was that because of the disk, obvious the fact that the planets are in a plane suggests that they formed out of gas within the disk. And so it seemed very natural that a little bit of rotation would lead to a disk, and then the gas in the disk would somehow coagulate into the planets. So that was a very natural model, very, very sensible. But it ran into objections because most of the mass solar system is in the sun. But the sun has almost none of the angular momentum. So there was no way, they couldn't understand how it would be that you could get if the sun to have all of the mass but none of the angular momentum. So it's the angular momentum problem. And that problem was considered so acute that people actually started to think that the solar system formed because two stars had a close encounter, causing one star to have tidally stripped bits of star matter, which then stayed in orbit and formed the planets by some extraordinary means.
Amazing, actually.
It's amazingly stupid.
In the 1930s, they were still considering stars passing by one another, and part of the sun was pulled out, and this sort of hot gaseous material then condensed and formed planets. It took Lyman Spitzer, I think, to point out, he said, well, no, because when you pull off the gas from the sun, it will actually disperse and go away. It won't form a planet. Okay, yes, that's a good point. So, yeah, it was, by today's standards, these ideas are extremely naive.
But they were preferable to find the notion that they somehow would get the angular momentum out of the gas from the sun.
So, in fact, it's a cottage industry unto itself, applying the MRI or trying to understand MHD processes in protostellar disks. The problem is, I've written a couple of reviews on this, in fact, that protostellar disks are big, which means the sort of velocities are kind of small and the shear is relatively small. It doesn't heat very well. They're big and they're cold and they're dusty. And this is not an ideal medium to have a lot of charge carriers. It also is a place where you have to take into account the full complexity of magnetohydrodynamic equations, including things that have names like ambipolar diffusion and Hall effect. And the property, I think in my talk I mentioned that it's kind of a miracle that we can do the magnetic problem. We can do it because of some very powerful simplifications. Ideal conductivity and Faraday's law of induction. Well, ideal conductivity doesn't work very well. It doesn't work rather badly in protostellar disks. You really have to come to grips with a lot of messy equations. And then chemistry, molecules. It's a big job. But nevertheless, it's kind of a consensus model that people work with. And that is that the inner part of the solar nebula is likely to be reasonably prone to the MRI magnetic couple hot enough. The outer part, sort of beyond kind of the radius of Neptune, round radius of Neptune, is also likely to be reasonably well magnetized because it's not very dense in combination. But there's an inner kind of region, now called colloquially dead zone, where the disk is probably not strongly magnetically coupled, at least not near the midpoint. And so people are interested in two-dimensional structures. So the answer to your question is that this has occurred to us to apply it to the solar nebula, and it's very much an active research program in progress.
Thank you very much. Questions, please? Yes.
Thank you for the talk, excellent talk. May I ask a question to Professor Holly? You have done so many beautiful models, simulations. To my very limited knowledge, we don't know about the black hole. Even light cannot escape in the region of black hole. So, in fact, how do you know? Because you may not have measurement for the magnetic field strength near the black hole. But how do you verify your simulation with the measurement? Do you have any evidence, or how do you verify?
He asked you that.
Well, as far as the black hole goes, I start with the assumption that Albert Einstein was right, and used a fixed Kerr metric for a rotating black hole. So I don't test that. Although there are other people who actually use numerical techniques to evolve the full equations of space-time and observe the formation of black holes or even collisions of black holes, production of gravity waves. That's a whole other area of research which is very, very interesting. But the question then is, in our simulations, basically, the only way to verify them, at least against nature, is to connect the results of the simulations to the observations. We observe light from accretion systems. We observe X-rays. We can observe time variability from those X-ray systems. We can observe multiple systems and to understand them as an ensemble. We know what the properties they exhibit, and we can compare those to the properties that we see in the simulations. One area of research that's very interesting is the relationship between the maximum temperature in the disk and the expected spin in the black hole, because the equations of general relativity tell you that the inner edge of the disk will be deeper into gravity for high spin cases, and the deeper you are, the stronger the gravitational forces and the greater the energy available, so that a rapidly rotating black hole can produce a disk that's much more energetic and much hotter than a non-rotating black hole. And so in the simulations, we've looked at accretion disks around non-rotating and rotating black holes to see how the maximum temperature changes. And people have looked at binary systems where they think they have a good disk that they can observe, and they've done ensembles of the different sorts of maximum temperatures, and they see, in fact, there's a range of maximum temperatures which would be consistent with the sort of expectations you'd have from the models and the theory. But in all fairness, at this point, that's sort of you can't get a conviction in a court of law on that evidence. It's sort of circumstantial evidence, but it shows how one can try to get from the simulation to the observables. The other thing you can do, which is not related to the observable, is simply rely on multiple groups with different numerical techniques and different codes to examine these problems and see whether basically the results are reproducible by different groups and different codes.
Yes.
Excuse me. I can never think of magnetic fields without thinking of associated currents. In the weak instability case, are these magnetic fields self-consistently built into the modeling? Where does the field come from?
Well, to answer to your first question is yes. They're built in self-consistently. Curl B is equal to J. That's part of the equations that we solve. As to the origin of magnetic fields in the universe, that's one we haven't tackled yet. As a practical matter, if we're studying a binary system, we take it as sort of observationally given that the material accreting from an ordinary star will be magnetized, and then ask what will happen to the magnetic field self-consistently when it's in the disk. For something, people who want to do simulations in the MRI in the galaxy, another cottage industry, they're more directly interested in studying dynamo processes per se, although starting from kind of a The zero field medium, the one that's magnetized, is still an ongoing challenge. But for the most part, we simply take it for granted that magnetic field is present, which is not a particularly radical assumption. It would be far more radical to say, well, there's no magnetic field there, zero, we're going to do the hydrodynamics. There you have to justify yourself.
Could I also ask about the jet fields? These are much greater fields. The currents that give rise to these are very close to the black hole. Is that how I would understand it?
Yes, and that's why if you didn't have the matter, if you didn't have the accretion disk, you wouldn't have the current available to maintain those fields. So if you took all the matter away, that field configuration, it doesn't remain that way. It radiates electromagnetic waves away. It's gone. So the disk plays the important role of maintaining the currents that maintain that field. But you don't need much of a disk. This was something that Roger Blanford and Newton and others a number of years ago pointed out that you can still have a strong radio jet with a rather low luminosity disk, because the disk could support the currents that kept the fields and the energy was coming from the black hole.
But you do make a good point in the sense that you do need to be careful when you set up your initial conditions to look at the currents, to make sure that you're not setting up a situation where you have an accretion disk and then there are big Helmholtz coils carrying the currents a huge distance away from the disk and setting up. So you're right in that you can't just choose whatever magnetic field you want and then let it rip. Some thought has to be given to keeping the currents embedded in the disk, or at least accounting for them in that.
Yeah, and there are differences in the simulations. Of course, the answer is very easy. The currents or the fields are there because I put them in at the start. In the case of the shearing box, for example, it's local, and there's sort of two categories. One where the currents are actually external to the box and can't be changed because they're not part of the simulation. And the others are ones where they're internal to the box and are subject to evolution. Maybe you would like to know more about Salina, Kansas?
Yes. Anything. Personal lives or freelancers? Yes, please.
I wonder whether MRI is an inevitable consequence of magnetized accretion disk. If you run a MHD simulations without knowing the linear instabilities in the first place, will you get MRI anyway?
Generally, yes. Well, to me, a famous story. The MRI was already, in retrospect, seen in simulations in the 1980s, but not understood. There was a case, a colleague of ours, Jim Stone, was uncovering it. This is not, was it at the lunchtime talk where you mentioned this?
Yeah.
Where essentially he was putting in a very weak magnetic field in the disk, just to make sure the code was working okay, and you expected to see the field get wrapped up and not do much. He put it in and the disk just sort of collapsed. That's what happens in 2 dimensions with the MRI. Oh, that's some kind of a bug. It works better with a stronger magnetic field. Do that case and I'll figure out what's going on later. And then there were, in the 80s as well, there was a Japanese group that actually published simulations of an accretion disk with the MRI going great guns, causes in 2 dimensions. It doesn't go with the turbulence necessarily. You can get peculiar, what we call channel solutions. Some of the disk going in, some of the disk going out, and then unless you can sort of mix it in the 3rd dimension, it just races off. And that was in the published paper without comment. So the answer is yes. Even if you don't study our papers, which you should do, and you just put a magnetic field in and run it, you will find the MRI, unless you put in a strong magnetic field and other things.
That's the beauty of numerical simulations, that will do, assuming you've written their code correctly, it will give you the answer whether you understand it or not.
Whether you want it or not.
It's like looking in the back of the text.
Yeah, that's it. Right. It's like peeking in the back of the book.
How would this scenario be affected when dark energy or dark matter is taken into account for the accretion disk?
How will the accretion disk be affected by dark energy or dark matter?
Yes.
Well.
Well, for galactic disk, the dark matter presumably is what is responsible for the kind of rotation curves as you see these flat rotation curves are in dark matter. But as far as I know, once you specify the potential for the disk to rotate in, the dark matter kind of disappears from the evolutionary process. As the dark energy, they, as far as I can tell, have nothing to do with accretions.
Unless the equation states the great rate. It's unlikely, but in which case dark energy will destroy everything.
Right. And the enormous shear in the universe, barring unforeseen circumstances, it's on the wrong scale for execution.
Hi. I have a question on the super hot region in the vicinity of the black hole, of course, outside the horizon. Will the pair production process because of the super hot region, the intense radiation, will the pair production process influence your model, the plasma model? Because you introduce some new charged particles into the system, and this depends on the temperature and the radiation density, radiation energy density.
Is that a question for me?
Yes.
Which one should I ask? I mean, I'm not sure if this model includes that kind of thing in the super hot
I'm not sure
region.
that it'll have much effect on the MHD because these disks are at this point 100% ionized. Adding more charge carriers due to pair production isn't going to change that situation. You get pair production in a protostellar disk by a trick. That would be interesting. But generally, as you say, this is an extremely exotic and high energy phenomenon. And in terms of it having sort of a direct influence on the MHD process, it's certainly not going to affect the ionization balance or make it any more easy because it's already an excellent conductor. Could do other things in the dynamical nature, but in terms of directly affecting the magnetohydrodynamics, it's not an important process.
But it probably is important for understanding some aspects of jets.
Yeah.
And these models don't include that.
Okay, maybe we'll have one last question. Last chance. Someone? Yes, please.
Okay. I'm wondering that if we are talking about the disk model, so shall it be influenced by its nearby disk in the universe? I mean, if there are two galaxies, and in the center of the universe, there should be more galaxies, more condensed, more dense than the outliers of the universe part. So if the disk model on its rotation will be influenced by its nearby neighbors.
I'm sorry, I'm having a little trouble.
Maybe I confused you.
Question.
For example, if there are two galaxies, one is next to the other. So if the
two galaxies, one is next to the other.
Yes, will they influence each other for the simulation and that?
So there are two. So your question is, there are two galaxies right next to each other.
Yeah.
And you want to study MHD turbulence within the galaxies? Does the fact that there's a galaxy nearby they'd have to be so nearby that your primary interest would be gravity, I think. And there you'd be looking more at tidal interactions. So I don't think you would have a situation where you have kind of two galaxies that are just sort of sitting there being happy, normal spiral galaxies. And the gravitational field of one somehow changes the rotation curve of the other, and so that makes the MHD physics change. That's not a situation that would be able to maintain.
Because I'm not in this background, but I heard that sometimes two galaxies will combine together and the black hole inside each galaxy will combine together, but I'm not sure.
Yeah,
So,
if you have two galaxies that come together, I mean, the galaxies merge,
yes.
and you have tidal stripping, but the black holes will end up merging as well
Yes.
eventually, and when that happens, they spiral together, they produce enormous amounts of gravitational radiation, and it's expected that they would produce some sort of photons, electromagnetic signature as well, from surrounding gas. And that's an area of research. We're not sure what that, right now we're not really sure what that electromagnetic appearance would be for colliding black holes.
Thank you very much.
Thank you very much.